All right, here we go. We're looking with numbers 8 through 10 from the summer work. The figure below shows a graph of velocity. So this is velocity. That's also known as a rate. And it's measured in miles per hour. Here's our actual function. T is hours and V of t is miles per hour. Estimate the definite integral of V of t with respect to time for 0 to 1. So here's 0 to 1. So we got some interesting stuff going on here. They didn't say exactly how. I'm curious to see if we have that stepped out later. Nope. So it's just leaving it up to us. So I'm going to split this up into some shapes. So I'm going to start with a rectangle. This looks pretty close to a rectangle here. And the area of this rectangle is going to be 0.8 times 20. Now I can do a couple of triangles. So if I look at this one, it looks like I could do this triangle and this triangle here. Or actually, that's more like a trapezoid. And I got this triangle here as well. So let's start adding all these pieces together. This triangle here would be 0.3 times 15 and 0.3 times 15 high. And here we got 0.2 times 15. And then this last one again is 15, but it's going to be 0.3 again. So we got two of those. And down here on the bottom one, this is 0.2 times 20. All right, so let's add all these together. So this first one, the big box rectangle, 8 times 20 is going to be 160. So this is going to be 16 for this big box. For this one here, 3 times 15 is 45, but it's really just 4.5 because we're moving the decimal over. This next one is 2 times 15, which is 30, but again, we got to move that decimal over, so it's 3. The last one again here, the last triangle, this is 4.5 as well. Oh, it's not really the last one. Here's the last one. 2 times 20 is 40, but this winds up just being 4. So we got 16 plus 4, that's 20. 4.5, 4.5, that's 9, and 3, that's 12. So up top we got 12, down bottom we got 20. Put those together. Looks like we got 32. Now we were multiplying miles per hour times hours, which gives us miles. So this is really miles here. That wasn't too bad. Now later on, I'm actually going to show you guys how to check that and see if that's a close guess or not. This I would guess is actually a little bit under because some of this blue shaded area that I'm putting in here we did not include in our calculation because straight lines and curves don't always match up exactly. Alright, let's look at number 9. Let's put some concepts together. Okay, so James sits atop a sliding board. He's sliding down this board all the way to the bottom. It's one of those big slides at the water park. At time t equals 0 seconds, he pushes off. So he's not going anywhere until after 0 seconds. That's when he starts to speed up all the way until the bottom. His velocity is measured in feet per second, and it's given right here, 20 sine 0.252. It says, how fast is he going when he hit the water? So it looks like he stops right here. So here's where he hits the water. And if he's hitting the water there, it's asking you how fast was he going. It looks like he was going 20 feet per second. At approximately what rate was his speed changing at t equals 2 pi? Well, so it's asking the slope of the rate. How fast was his rate changing? How fast was the rate of change changing? To determine that, let's use the actual function. So let's go back here to our calculator. And in our calculator, we're going to type in this function into our y1. We'll use it there. So it's going to be 20 times sine times 0.25 times x. We don't have t, so we're going to use x. So, and we're going from, it looks like about 0 to 7 or so. So let's go ahead and set that up as well. We'll go from 0 to about 7. And our y maximum is not nearly 180 feet. It looks like it's more like 20. So let's type that in. So here's our graph. That looks pretty similar to what we have there. Okay, and at approximately what rate was he going when t equals 2 pi? Well, that means I got to find the instant slope. Now, if you guys remember, we were actually doing this using the graph calculator. So if we go down to 6, that's our dy dx, that's our instant slope. Now 2 pi, I don't know if you can put that in here. Let's try 2 times, and we're going to put pi, second pi. Let's see if that works. Does it? It does. Whoa, that's interesting. Our slope is 0. In fact, it's entirely flat at 2 pi. So that means that the slope equals 0. Does that mean that he wasn't going fast at all? No, he was going 20 feet per second, but it wasn't changing. It wasn't going up. It wasn't going down. It was staying right at 20 feet per second, just for that momentary pause. Explain a special name for answer B and why this answer makes sense. Okay, well, we do have a name. It's for the rate or the slope of velocity. We got a name for that. It's called acceleration. Why? Just that's the word that we use. What's the approximate length of the sliding board? So what they're really asking is, we're going up this board and way up the hill, and how far did we go? Well, you got to remember that distance equals rate times time. And now rate is not constant, but if we found the area, like we did in problems earlier, the area is going to equal that distance because the area is our rate times the time. So let's try and find this area. It looks like we got a triangle, maybe about this big, it looks like. So 3.5 seconds. And then we got another triangle here. And the last bit is a rectangle. So let's try and figure out what these boxes are. So this box here is going from 6.5 to the end, which is 2 pi. So 6.5 to 2 pi. 2 pi is going to be 6.28. Is that what it is? Oh, that's 5.5. This is 5.5. So this box up here is going to be 5.5 to 6.28. How much is that? It's going to be 0.5 plus 0.28. So that's 0.78 for that length. And this height here is 4. Now the big box goes from 3.5 to 6.28. So that's going to be 2.78. How did I get that? Because it's 2 less than 5.5. So it's just a little more. This units right here are 2. Now this one goes from 0 to 3.5, so that's 3.5, and the height is 16. The height is also 16 for the big box. So let's calculate these areas. We got 3.5 times 16 divided by 2. That's the first triangle. Whoop. Looks like we gotta quit. 3.5 times 16 divided by 2. I think that's right. There we go. So that's 28. So this right here is 28. The next box, which is 2.78 times 16, let's see how much that is. 2.78 times 16. That's 44.48. 44.48. Now let's look at top here. We got 0.78 times 4. 0.78 times 4. It's going to equal 3.12. 3.12. And the last triangle, which is, how much is this? That's going to be 2 times 4. So, oh, that's easy. That's 8. So we got 28 plus 8 plus 3.12 plus 44.48. So let's just put those numbers in here. 28 plus 44.48 plus 8 plus 3.12. That's the areas of all the little pieces that we added up. And that equals our distance, because the area of a rate is going to be some type of accumulated value, in this case, distance. Number 10. A new boat when accelerated from a standing start, travels with velocity blah. That's measured in feet per second. So it says draw the graph. All right, well, I guess that means we have to graph it with our calculator, then draw it. So we'll go to our y equals. We're going to clear this one. It's going to be 75 times, and then, excuse me, 1 minus 0.849, but that's going to be raised to a power, to the x. So to the x. There we go. Close that off. Looks like our window goes from about 0 to 20. 0 down to 20. And our y values, how far do our y values go? From 0 to about 80. So we need to raise our y value up to 80. And since we're going up to 80, this is counting by 5s. Let's do that as well. If you notice that vertical part of the graph is counting by 5s. And the horizontal part is counting by 2s. So now we're going to have marks that look just like this graph here. That'll make it easy for us to sketch. So there are those things. Let's graph it now. That looks pretty close. All right, so that's not too hard to draw. Looks like it starts at 0, ends at about 75 or so. So it looks like we're going to have something that looks like this. It says how far, okay, draw the graph. Approximately when will the boat reach 55 seconds? So it looks like maybe at about 10 seconds. But let me check my graph too and see if that looks like what it is. At 10 seconds, so 2, 4, 6, 8, 10. Is that about 55? It's kind of hard to tell. But let me try and check the value. Second, calculate a value. I'm going to plug in 10. Is that about 50? That's about 60. So it's a little bit less than that. It looks like I'm a little bit off on my graph. Maybe 8. Let's try and calculate it at 8 seconds. So if we plug in 8, does that equal 50? That's closer. Let's try and calculate it at 6. So we calculate the value, plug in 6. That's 46. So maybe in between. So second, calculate 7. Whoops, that's not what I wanted. Clear. So I want to do second, calculate. I want to calculate the value, but I want to type in 7 here. That's what I want. So about at 7. So it looks like at 7 seconds. About how far did the boat travel when it reaches 55 feet per second? So we're looking at this triangle here. And if you imagine that it's about 55 tall, and it's actually more about like this. Looks like the picture should look more like that. So we have this triangle that's 55 feet tall and 7 horizontal. So we got triangle. 7 by 55. We can find the area of that triangle. Let's try that. Okay, so then that means we're going to calculate 7 times 55. Whoops. We want to go back to our calculation screen. 7 times 55. And it's a triangle, so we got to only take half of it. 192.5. It looks like it's 192.5 feet. At approximately what rate is velocity changing? Velocity is changing at a rate. That's called acceleration. So we're looking for the slope of this velocity at 55. Well, let's just calculate that on the graph. We have a button that does that. So we go second, calc. We're going to do the dy dx. That's our slope at about 7 seconds. It looks like the slope's going to be about 3.9. So about 4 feet per second, or second squared on the bottom, you could say. It's called acceleration, by the way. And that's it for lesson 2. We're done with this. Moving on to lesson 3, coming up soon. But for right now, that's the end of lesson 2. And the crowd said, yay!